Let us consider a classic natural process, for example, the expansion of the universe in itself. Okay, so if we consider that the universe is expanding as a whole, and if we plot the disorderliness of the universe in an XY diagram where the x-axis represents the time passed and the y-axis represents the measure of disorderliness of the universe, then we can say that as time passes, the disorderliness, let's define this as d, the disorderliness of the universe kind of increases as well, whether it be in a linear form or in an exponential form. Whatever that might be, the disorderliness of the universe increases as the expansion of the universe takes place along with the increase of time. Okay, if we are clear with this idea, then we define entropy as denoted by the letter S, entropy as a measure of disorderliness. Okay, so let us recap what we have learned till now. The universe is expanding, which is a natural process, of course. And as the universe expands, the time increases as well. And if that really is the case, then the disorderliness of this natural process kind of increases. And as disorderliness of this entire system increases, the entropy of the system increases as well. If this actually stands true, then we can establish a relationship between all natural processes, its time, and its measure of disorderliness as described by the concept of entropy over here. This is basically what the second law of thermodynamics says. The second law of thermodynamics basically says that for all irreversible reactions or natural processes, the change of entropy of a system tends to increase as with the increase of time. Over here, you can see that all natural or irreversible reactions are taken into account. Why is it really the case? Well, all natural phenomena or irreversible reactions in this universe are correlated to each other, which means that pretty much every single phenomenon in this universe that we actually observe with our eyes are all irreversible reactions. And for this, we can mathematically define all irreversible reactions and their change of entropy in such a way that their increase of entropy is always positive. Where this ds over here represents the change of entropy. Okay, so we are done with the concept of natural/irreversible reactions. Then what might be the case for reversible reactions? Well, the second law actually says and extends up to reversible reactions, saying that for reversible reactions, the change of entropy of all systems is basically zero with the increase of time. And of course, mathematically, we can say that for all reversible reactions, the ds, which is a change of entropy, is basically zero. Now, let's delve deep into the concept of reversible reactions. Well, in the universe that we live in, 99.99% of natural reactions or phenomena that we observe with our naked eyes are all irreversible. And the rest of the reactions and phenomena that we take into consideration on pen and paper are theoretical and sometimes considered as reversible. So these are all theoretical concepts. So reversible reactions don't actually occur in our surroundings, and we only take those into consideration when we deal with theoretical stuffs. So these aren't actually a thing, okay? So here we are dealing with the second law of thermodynamics, right? Added to this, we can also define entropy in terms of the third law of thermodynamics, which is an added fact to this, which is an extended form of this. Well, if you can remember, then we have discussed the change in entropy in a mathematical way, defining the change of entropy ds as of this form, right? This is the integral of dq over t, where t is the temperature, right? Okay, so the third law of thermodynamics actually says that the change in entropy approaches an approximate constant value as this temperature of the system reaches or approaches an absolute zero condition. Well, as you can see over here, that if t actually approaches 0, then this entire value of ds becomes invalid or undefined, right? So from there we have concluded this third law of thermodynamics, that ds over here approaches a certain constant value as t over here approaches absolute 0. Well, that's all for today then.